Breakthroughs in technology and engineering, shaping the future. The 21st century has witnessed an unprecedented acceleration in technological and engineering advancements, fundamentally reshaping industries, economies, and daily life. From energy storage to telecommunications, sustainable energy solutions to artificial intelligence, AI, and robotics, recent innovations are not only solving long-standing challenges, but also opening new frontiers for human progress. This essay explores 4 transformative breakthroughs in technology and engineering as of September 2025: solid-state batteries, 6G chip development, transparent solar windows, and advancements in AI and robotics. These innovations promise to redefine transportation, communication, energy production, and human-machine interaction, with far-reaching implications for society and the environment. Solid-state batteries, powering a sustainable future. The promise of solid-state technology. Solid-state batteries represent a monumental leap in energy storage technology, offering significant improvements over traditional lithium-ion batteries. Unlike conventional batteries, which rely on liquid electrolytes to conduct ions between the anode and cathode, solid-state batteries use solid electrolytes, such as ceramics or polymers. This fundamental shift results in higher energy density, enhanced safety, and longer lifespans, positioning solid-state batteries as a cornerstone for the future of electric vehicles, EVs, renewable energy storage, and portable electronics. The higher energy density of solid-state batteries allows them to store more energy in a smaller space, enabling EVs to achieve longer ranges without increasing vehicle weight. For example, companies like Toyota and QuantumScape are developing solid-state batteries that could power EVs for over 600 miles on a single charge, compared to the 300-400 miles typical of current lithium-ion powered models like the Tesla Model 3. Additionally, solid electrolytes are non-flammable, significantly reducing the risk of fires, a persistent concern with liquid electrolyte batteries, as seen in rare but high-profile EV battery fires. Real-world applications and challenges. The implications of solid-state batteries extend beyond transportation. In renewable energy systems, where efficient storage is critical to balancing intermittent supply from solar and wind, solid-state batteries could enable more compact and durable grid-scale storage solutions. For instance, integrating these batteries into microgrids could ensure reliable power in remote areas or during outages, as demonstrated in pilot projects in regions like California, where wildfires frequently disrupt power supply. However, challenges remain. Manufacturing solid-state batteries at scale is complex and costly, primarily due to the need for precise material synthesis and assembly. Current prototypes often face issues with dendrite formation, tiny metallic growths that can cause short circuits. Companies like Solid Power are addressing this through novel electrode designs, but widespread commercialization is still projected to be a few years away, with 2027-2030 as a realistic timeline for mass market adoption. Broader impact. The transition to solid-state batteries could accelerate the global shift to clean energy. By improving EV affordability and performance, they could reduce reliance on fossil fuels, cutting greenhouse gas emissions. The International Energy Agency estimates that EVs could account for 60% of global car sales by 2030 if battery innovations like solid-state technology lower costs. Moreover, longer-lasting batteries reduce the need for frequent replacements, decreasing the environmental impact of battery production and disposal. 6G chip development, the next frontier in connectivity. revolutionizing communication. The race to develop 6G technology is poised to redefine telecommunications, promising internet speeds up to 100 times faster than 5G. In 2025, researchers unveiled a compact 6G chip capable of operating at terahertz frequencies, 100 to 300 GHz, a significant leap from the millimeter wave bands used in 5G. This chip, developed through collaborations between institutions like MIT and industry leaders like Nokia, leverages advanced semiconductor materials like gallium nitride to achieve ultra-low latency and unprecedented data transfer rates. For context, 5G networks typically offer download speeds of 1 to 2 Gbps, enabling applications like autonomous vehicles and augmented reality, AR. 6G, however, could achieve speeds exceeding 100 Gbps, facilitating near instantaneous data transfer for applications like holographic communication, real-time brain-computer interfaces, and massive Internet of Things IoT ecosystems. For example, a 6G-enabled smart city could process data from millions of sensors in real time, optimizing traffic flow, energy use, and public safety, enabling transformative applications. The potential of 6G extends beyond speed. Its ability to support ultra-reliable, low-latency communication, URLLC, could revolutionize industries. In healthcare, 6G could enable remote surgeries with haptic feedback, allowing surgeons to operate on patients thousands of miles away with precision. In manufacturing, 6G-powered IoT networks could enable fully autonomous factories, where machines communicate seamlessly to optimize production. For instance, Ericsson's 6G research envisions digital twins of factories, where real-time data from 6G networks creates virtual models for predictive maintenance. Challenges and future outlook. Despite its promise, 6G faces significant hurdles. Terahertz waves have shorter ranges and are easily blocked by obstacles, requiring dense networks of small cells and advanced beam-forming technologies. Additionally, global standardization and spectrum allocation for 6G remain in early stages, with commercial deployment not expected until around 2030. Geopolitical tensions over semiconductor supply chains, as seen in recent US-China trade disputes, could also delay progress. Nevertheless, 6G's potential to create a hyper-connected world is undeniable. By enabling seamless integration of physical and digital systems, it could drive innovations in smart cities, telemedicine, and immersive entertainment, fundamentally transforming how we interact with technology. Transparent solar windows, harnessing energy with elegance. A new paradigm in solar energy. One of the most visually striking innovations in renewable energy is the development of transparent solar windows. These windows, coated with a novel material that redirects polarized sunlight to solar cells embedded at the edges, generate electricity without compromising transparency. Unlike traditional opaque solar panels, this technology, advanced by companies like Ubiquitous Energy, allows buildings to become self-sustaining power generators while maintaining aesthetic appeal. The coating works by selectively absorbing ultraviolet and infrared light, wavelengths invisible to the human eye, while allowing visible light to pass through. This redirected light is converted into electricity by photovoltaic cells, achieving efficiencies of around 10–15%, comparable to early-generation solar panels. For example, a skyscraper with transparent solar windows could generate a significant portion of its energy needs, reducing reliance on fossil fuel-based grids. Applications and environmental impact. transparent solar windows have transformative potential for urban environments. High-rise buildings, which consume vast amounts of energy, could offset their carbon footprint by integrating this technology. A pilot project at Michigan State University demonstrated that retrofitting existing windows with solar coating could power lighting and HVAC systems in office buildings. Additionally, the technology can be applied to car windows, greenhouses, and even the smartphone screens, creating new opportunities for decentralized energy production. The environmental benefits are substantial. By enabling buildings to generate their own electricity, transparent solar windows reduce greenhouse gas emissions and alleviate pressure on aging power grids. According to the U.S. Department of Energy, buildings account for nearly 40% of global energy consumption, making this technology a critical tool in combating climate change. Challenges and scalability. Scaling transparent solar windows faces challenges, including high production costs and the need for durable, weather-resistant coatings. Current efficiencies, while promising, lag behind traditional solar panels, 20 to 25% efficiency, necessitating further research into advanced materials like perovskites. However, as production techniques improve, costs are expected to decline, making the technology viable for widespread adoption by the early 2030s. AI and robotics, redefining human-machine interaction. AI innovations. Artificial intelligence is evolving at a breakneck pace, with recent breakthroughs pushing the boundaries of creativity, efficiency, and interaction. One remarkable development is AI that paints with light, using minimal energy to create intricate visual displays. This technology, pioneered by researchers at Stanford, manipulates light waves to project dynamic images, with applications in low-power AR displays and energy-efficient advertising. Another breakthrough is AI models capable of generating lifelike 3D animations from single images. For example, Meta AI's recent model can transform a 2D photo of a dog into a 3D animation with realistic movements, opening new possibilities in entertainment, gaming, and virtual reality. This technology leverages generative adversarial networks, GANs, to extrapolate depth and motion, achieving results once thought to require extensive manual modeling. Robotics advancements. In robotics, human-like tactile perception is a game changer. Researchers at ETH Zurich developed robotic grippers with sensors that mimic human touch, enabling robots to handle delicate objects like eggs or glass without breaking them. This technology is already being deployed in industries like logistics, where robots sort packages with precision, and in healthcare, where robotic assistants aid in surgeries or patient care. Soft robotics, inspired by biological systems, is another frontier. For instance, MIT's soft robotic fish, equipped with AI-driven navigation, can explore ocean environments to monitor marine ecosystems without disturbing wildlife. These advancements highlight robotics' growing role in addressing complex challenges, from environmental conservation to medical assistance. Industry transformations. The convergence of AI and robotics is reshaping industries. In healthcare, AI-powered robotic surgeons, like those developed by Intuitive Surgical, perform minimally invasive procedures with unprecedented precision, reducing recovery times. In entertainment, AI-driven 3D modeling is streamlining content creation for films and video games, as seen in companies like Unity leveraging AI to automate animation pipelines. In manufacturing, collaborative robots, cobots, work alongside humans, enhancing productivity while maintaining safety. as demonstrated by universal robots deployments in automotive factories. Ethical and societal considerations. These advancements raise ethical questions. AI's ability to generate realistic animations risks misuse in deepfakes, necessitating robust detection tools. In robotics, automation could displace jobs, requiring reskilling programs to mitigate economic disruption. Additionally, ensuring equitable access to these technologies is critical to prevent widening global inequalities. Conclusion: a vision for the future. The breakthroughs in solid-state batteries, 6G chip development, transparent solar windows, and AI and robotics represent a convergence of innovation that promises to address pressing global challenges while unlocking new possibilities. Solid-state batteries could power a cleaner, more efficient world. 6G could create a hyper-connected society. Transparent solar windows could turn cities into renewable energy hubs. And AI and robotics could redefine how we interact with technology and each other. However, realizing this potential requires overcoming technical, economic, and ethical hurdles. Collaboration between researchers, policymakers, and industry leaders is essential to ensure these technologies are deployed responsibly and equitably. As we stand on the cusp of these transformations, the choices we make today will shape the trajectory of human progress for decades to come. By embracing these innovations with foresight and responsibility, we can build a future that is sustainable, connected, and inclusive.